Okay, so we've been talking about integration, right? We defined the Riemann integral at the beginning of last week and said, okay, for that we have to look at all possible partitions and all possible Riemann sums over those partitions, so all the different choices of CJ. And then last class we said, wouldn't it be easier if we could just stick with simple partitions, and instead of doing all these different Riemann sums, maybe just look at the extreme ones, so to speak, the upper sum and the lower sum, and maybe that's good enough. So we want to keep going on that track and show that actually that is good enough. So this is existence of the integral. Or other criteria for showing that the Riemann integral of a function exists. Okay, so the idea is we're looking at upper and lower sums, right, on just a subset of all possible partitions. And our question is, can we find some other partition out there, maybe a much more refined partition that nevertheless gives us a value of a Riemann sum that is either much larger than the upper sum we came up with or much smaller than the lower sum we came up with? That would be bad. That would mean we don't have convergence of these Riemann sums. So turns out as long as these upper sums and lower sums on simple partitions behave themselves, we're actually in really good shape. So here's the result. Let's let f be bounded on our interval. Remember, that's always a reasonable thing to assume when we're talking about Riemann integrable functions, because we proved that if a function is Riemann integrable, it's automatically bounded. So there's no restriction really putting this here. And now we're going to suppose that for every epsilon greater than 0, there exists some partition P of the interval such that, and now what we're going to do is look at the upper and lower sums on this partition. And what we're going to assume is that these upper and lower sums give us values that are very close to each other. So such that the difference between the upper sum and the lower sum can be made less than epsilon. Okay, if we can do this, then we can conclude that f is integrable. Okay, so as long as we can find a simple partition, say a uniform partition, such that the upper and lower sums can be made arbitrarily close to each other, we're good. And moreover, we can figure out fairly easily then what the value of the integral is. It's going to be the same as the upper integral and the same as the lower integral. So we take all these upper sums and we find the smallest one, or we take all the lower sums and we find the biggest one. Those are going to give us actually the value of the integral. So we're going to conclude that the integral of f is equal to the upper integral, and it's also equal to the lower integral. All right, and we saw last class that we could typically work out what these upper and lower integrals were using, again, very simple partitions. Even though the definition involves more general things, we could work them out using simple partitions because we proved a couple properties of these things. Before I go on, are there any questions about just the statement of the theorem? Does it make sense what this is saying? Okay. So let's see if we can convince ourselves that this is true now. All right. So what we want to do is we're in this setting. We need to show that this agrees, that this function f agrees with the usual definition of Riemann integration, which means that we pick an epsilon greater than 0. We have to show that there's some delta out there such that for any partition that's sufficiently refined with norm less than delta and any Riemann sum, any choice of CJs, right? Our Riemann sum is going to be close to the value of the integral. So I'm going to let this be the value that we're trying to show it's equal to. That's a number, and we know it's a well-defined number. Okay, so let's choose our epsilon greater than 0. Okay, we have an idea what our goal is, and we also know that we have some information we can use. We know that we can find a partition such that the upper sum and lower sum are close to each other. So I'm going to write down what we know. So we know that somewhere out there exists a partition, P, which is x0, x1, down to xn, such that the difference between the upper sum and the lower sum is less than, I'm going to actually call this less than epsilon over 2, just to make things work out neatly in the end. You don't have to do that. Right, so we know we can make this difference less than any tolerance we like. We can make it less than epsilon over 2. All right, and then we're going to do our usual definitions, right? So as usual, we have capital M sub I is going to be the supremum of f on each of these little subintervals. Okay, little m is the infimum. Okay, and then I'm also going to let capital M without any subscript be the supremum of f overall. So the supremum in the entire interval, a to b, of the absolute value of f. All right, again, that's well defined because we've got a bounded function. Okay, two possibilities. One is that m is equal to 0. What does m equals 0 mean?
Constant function.
It's a constant function, right? F is just uniformly equal to 0. So if m is equal to 0, that means, right, the absolute value of f is always less than or equal to 0. So f itself must be 0 everywhere. This is an integrable function. All possible upper and lower sums that you care to write down are going to be equal to 0, right? The function holds, the result holds trivially. Okay? Okay, so the result holds. So what we need to focus on, where all the work is when m is actually a positive number. Okay, so again, we're in this case, we've got a bounded function. We happen to know a partition with this property, but now we want to show this function is Riemann integrable. That means we have to go back to the definition of Riemann integrability, and we've got to look at just a generic partition. Okay, so we need to look at a general partition. Okay, I'm going to call it Q. And again, this is a bunch of points. Call them Y. It has some norm that's less than delta, but we don't know yet what delta is. So we're going to say delta is still to be determined. Okay, so we have a generic partition, and then we need a generic choice of these CJs that live in each of these intervals. So we choose, as usual, any CJ belonging to yj minus 1, yj. And that gives us a generic Riemann sum. So we look at the Riemann sum. We call sigma as usual. We sum over all our little intervals in this partition. And we want to look at f of cj times yj minus 1. Okay, and now what's my goal? My goal is going to be to try to show that, right? As long as we pick delta right, so that we can find a delta that ensures that sigma, right, our Riemann sum, as long as things are sufficiently refined, our Riemann sum minus our candidate value of the integral is less than epsilon. Okay, we're comfortable with this. This is our, so I haven't really done anything yet. All I've done so far is I wrote down what I know, and I wrote down what we want to try to prove. Now we need to do a little bit of work to get there. All right, so we probably should have some restrictions on delta. Delta is probably not 1,000,000 or whatever, and in particular, we probably should try to relate delta to what's going on in here, or at least come up with some restrictions related to what's going on in here. And we know, just like when we were first learning limits, we can keep adding restrictions to delta. I assume delta is less than 1. Later, I assume delta is less than epsilon over 2, whatever. We can keep adding these restrictions on. That's OK. OK, so one thing I probably want to do is relate delta to the spacing that's going on in here. So we need restrictions on delta. So let me draw this cartoon off to the side. So we have some x0, x1, x2, x3, whatever it is. This has some norm. I'm going to guess that I want this partition to be refined, right? Making it more refined never hurts anything. So in particular, I'm going to require it to be at least as refined as the smallest gap in this partition. Okay? So the norm of this thing, the norm of this partition is the biggest gap, right? I'm going to look at the smallest gap and say I want to be more refined all the way throughout. So let's require it Q to be, in some sense, more refined, which you write down precisely what that means, throughout than P was. Okay, so in particular, if I define H to be the minimum of all of the xi minus 1, okay, and we're going to restrict to delta being no bigger than this h. Okay, so that's a choice. just to get started. Again, maybe we've refined this. Maybe we've taken this delta to be much smaller than we need it to be. That's okay. Again, it never hurts us to take delta to be too small. All right, secondly, we know that we need to do some work with this Riemann sum. We need to do some manipulations here to compare it to this number I. And it's reasonable that we should try to manipulate it in a way that we can write it in terms of this upper sum or this lower sum. Make these things pop out because we know something about these things. So right now, I'm summing over all of these j's. It would be really nice if I could write this in a way where I'm actually summing up over all of these xi's instead. Okay, so I have different things going on in here, right? I have maybe a y0, y1, y2, y3, y4, y5, y6, whatever it is. Instead of summing up over all of these, I want to try to batch these a little bit and sum up over the ones that live in this interval, and then sum up over the ones that live in this interval, sum up over the ones that live in this interval. We'll do this over a couple steps and try to make precise what's going on. We'll just say it would be nice to express sigma as a sum of, let's say over the intervals xi minus 1 to xi. And the reason is because we're trying to get it in terms of these original upper sums and lower sums that we got. So this is in hopes of extracting something that looks like S of Fp or little s of Fp. We need to extract those somewhere because that's the information that we were given that we have to work with. Okay, so what I need to try to do is sort of tabulate which of these guys live in the first interval, which of these guys live in the second interval, and so on. Let me draw the picture first. So I'm just going to draw one of these intervals. Say this is xi minus 1, and this is xi. All right, so maybe I have, maybe y9 lives out here, and y10, y11, y12, and so on. And I'm going to define n of I to be equal to the set of all indices such that yj lives in this interval. Okay, so in this picture, I look at the interval xi minus 1 to xi. This should be xi minus 1 to xi, sorry. And the guys that live in here are 10, 11, and 12. So in my example, n of I, this is y10 lives in there, so I put a 10, y11, and y12.
And each one of those is at least 1 point.
Oh, okay, good. That was my next question. Are any of these sets empty? Okay, and Zachary's already said no. Why are they not empty?
Because we have enough points spreading over the interval.
We have enough points spreading over the interval because I've required h to be less than delta, right? So this distance is at most delta, or at least delta, rather. So this distance here is going to be greater than or equal to h, right? Because I said h was the smallest possible distance between these x's, and each of this distance is going to be less than or equal to delta, which is less than or equal to h. So we know that there's at least one y in each of these intervals, and that's important. So each ni is non-empty. Okay, since we chose the norm of q to be less than delta, which is less than or equal to h, which is certainly less than or equal to xi minus 1. It's from the way we define these things. Right? This gap is always less than, strictly less than this gap, so one of these guys has to live in here. Okay, so we can always write down at least one number that's in here. I'm going to call that number p of I. There might be more than one. In this picture, there's more than one, but there's at least one. So let's let p of I be the smallest number in this set. Right? Every non-empty set of natural numbers has a smallest element, so we can write that down. There may be more numbers in this set. There may be only this one, but there's at least this one, which in this case is going to be 10. So my example, p of I is 10. Okay, so I'm going to use this relationship to try to take this Riemann sum, which right now I'm summing up over all the y's, and instead I want to sum it up over all the x's. So I'm going to break it up. Let's rewrite sigma as, okay, sigma was originally j equals 1 to m, f of cj, yj minus yj minus 1. Now we're going to try instead to sum up over all the xi's. Okay, so what I'm going to break it down into, I'm going to start with I equals 1, and I'm going to say which of these intervals has a right endpoint that ends in the first interval. And I'm going to write those down. And I go to I equals 2, and I'm going to say which of these intervals has a right endpoint that lands in here. I'm going to write those down, and so on. So we're going to break this up. We're going to say, let's look at all of the right endpoints that live in this interval. Okay, so j belongs to ni. That means if I happen to live in this interval, I'm going to sum over j equals 10, 11, and 12, and I'm going to let them be my right endpoints. So that means I'll get this interval, this interval, this interval. Okay, so this interval, and this interval. F of cj, yj minus yj minus 1. So we'll get all the right endpoints that land in here, all the right endpoints that land in here, all the right endpoints that land in here. I'm still summing up over exactly all of the same intervals. All of these are getting summed up. I'm just batching them. Okay, again, we know that each one of these sums inside here has at least one term in it, right? Because there's always at least pi here. And there may be more, but there's at least that one. So I'm going to break this up again into the term that I know is definitely there, and everything else, which might be 0, or it might make an additional contribution. Okay, so this is going to be equal to the sum I equals 1 to n. And now I break this up. I say, I know p of I works. So f of c pi times y pi minus y p of I minus 1 plus everything else that I left out, right? Which again, it might be nothing. It might be something. Okay, so everything else was all the j's that live in n of I, except not p of I. Okay, are we okay so far? Okay, so what do I know about these intervals? I know that this first interval, right, may go outside, be partly outside and partly inside my x interval. All of the rest of these are completely inside my x interval. Okay, so we know that ypi minus 1 to ypi may not be contained in the x interval. But all the rest of the yj minus 1, yj are going to be contained in this x interval. Okay, I'm going to use that information to try to bound all these terms. So let's try to bound all these terms separately. Let's maybe start over here. Okay, so for j belonging to n of I and not equal to p of I, what's the biggest this could possibly be? What's that? Capital M, so capital MI, exactly. So for all of those, right, those are all contained completely but in this x interval. So f evaluated anywhere throughout here is going to be bounded by the maximal or the supremum value of f in this interval. So this is certainly less than the supremum in xi minus 1 xi of f of x, which we called capital M of I. Okay, that bound won't work on this term, right? Because this term is in this interval, and the Cj might live between my x's, or it might escape from my x's. It might be something else. So for that guy, for f of c of p of I don't have this bound. The best I can do is say he's less than certainly the maximum value of f. Okay, again, this term overall is somewhat of a troublemaking term because he's sort of spanning two different x intervals potentially. But again, we can put bounds on things. What's the biggest this difference could be? Close, yeah? Delta, yeah. So we also know that y of pi minus y of p of I minus 1 is certainly less than delta. Okay, so I'm going to use this to come up with bounds on my sigma. The good news is I've brought in these mi's, which is what I want because I'm trying to get this all in terms of an upper sum because I know things about the upper sums over this simple partition. And then I have maybe some junk left over, but hopefully we've got tight enough bounds on it that we can at least control it. Okay, so let's put this all together. We have sigma is less than or equal to, okay, this first term. We said this was less than m, and this was less than delta. So actually, I can make this a strict less than m times delta. And then my second term is I equals 1 to n. This term was less than or equal to mi, times, and we have to add up all of the rest of these guys. Okay, this is getting simpler. I know that I want an upper sum popping out, which means I don't really want all this junk. I'd really like just an xi minus 1 here. How does this relate to xi minus 1? Yeah.
It's less than it.
It's less than it, right? So here, I'm just saying I'm adding up all of these intervals that live strictly inside of my x interval. So I'm adding up, I ignored this one that overlapped, pulled that out. I'm saying I'm taking the width of this interval plus the width of this interval. That's going to be less than the total width of this x interval. So this here is certainly less than xi minus 1. Here, on the other hand, I'm adding up a bunch of stuff, but it doesn't depend on I at all, right? These are just constant terms, m times delta. So I'm doing m delta plus m delta plus m delta n times over. So this I can sum up exactly. This is m times delta times n. This I get a bound on, and my bound says I'm adding up my mi, and I'm adding up the width of this x interval. Okay, so if I simplify this, I have my m delta n. And this is nothing but the upper sum of f over my original partition P, right? The one that I wrote down at the beginning where I said I have a simple partition where I know that I can control the upper and lower sums of f. This is exactly that partition, and this is exactly that upper sum. So this is precisely the upper sum of f over P. So this is pretty good, right? I'm trying to take my Riemann sum and relate it to the upper sum that I know things about. Ideally, I would like to say that it's close to this upper sum, right? We have an upper sum and we have a lower sum that are very close together. I want to be able to say that not only are they close to each other, they're close to the value of the integral. And that means I would really like sigma not to be less than s plus 10,000, right? I would like it to be less than s plus something little. So this is my question. Can we force sigma to be less than capital S plus something little, say another epsilon over 2? Can we do that? Okay, how can I do that?
Choose the delta.
Right, I just have to choose the delta, right? This is the same thing as back when we were doing limit problems. We always said we have this delta, we don't know what it is, we're going to decide it at the end. And when we get to this stage, we say, okay, if this is less than epsilon over 2, we can solve for our delta, right? Because m I don't have any control over. M is just the biggest value of the absolute value of f. N I don't have any control over. It was just the number of intervals in the partition you gave me. But delta I have complete freedom over. So the answer is yes, we can do this. We just require delta to be less than or equal to epsilon over 2mn. Right? Maybe delta already was, I'm not sure, but if not, we just say we're going to make it even smaller. Making it even smaller will still preserve it being less than h, not a problem. Okay, so what do I know? I know that this generic Riemann sum, as long as I refine my partition enough, I can keep this generic Riemann sum from exceeding the value of my upper sum by more than a tiny amount. Okay, so we know that. With this choice of delta, sigma is less than the upper sum plus epsilon over 2. And there's nothing really special about the upper sum here. I could have done the same argument, the same long calculation we just did in reverse, reversed the inequalities throughout, and I would have gotten a lower sum. So I could use the same reasoning. We're going to have that sigma is bigger than the lower sum minus epsilon over 2. Okay, so we have this lower sum and this upper sum that are very close together. And now we've shown that we can essentially sandwich sigma between them, or at least very close to being between them, as long as we take our delta small enough, as long as we take enough points when we do our Riemann sum. Okay, so let's see what this gives us. Okay, so as long as we take the norm of q to be less than delta, which now we have some conditions on it. We said should be at most h and should be at most epsilon over 2mn. What do we know? We know that, I just wrote this down, we can relate this to the upper sum. But better than that, we can relate the upper sum to the lower sum, right? We know that the upper sum is very close in value to the lower sum. So in particular, this is less than the lower sum plus epsilon over 2. Right? Because we said right at the beginning, I'm assuming that I can come up with a partition such that capital S minus little s is less than epsilon over 2. Right? Yeah, question?
For the bounding lower sum that we said?
For bounding which?
Well, we said if we use the same logic, we said
Yeah.
we can bound sigma
Yeah.
with the lower sum
Yes.
difference. Would that have given us an additional constraint on delta?
It will work out to be the same constraint on delta.
But with capital M or with lowercase m?
With capital, so what we'll have is f is less than capital M and it's bigger than minus capital M. So the sign flip will come in there, but it won't give us a different. It won't give us a different delta, because when I defined capital M, I defined it to be the maximum or the supremum of the absolute value of f.
I gotcha.
Yeah. If I just taken a capital M and a little m separately, then yeah, we would get something different. So capital S minus little s is less than epsilon over 2. That's why I could make this substitution in here. That was the thing we wrote down right at the beginning, the piece of information we were given. Okay, so this is the lower sum plus epsilon. Okay, we know that if we take lower sums, right, and relate them back to our lower integral, we're trying to get back to our lower and upper integrals. The lower integral was the supremum of all of these lower sums, right? We said all of these are underestimates, so let's take the biggest one. This is certainly less than the supremum of all of our lower sums. Which was how we defined our lower integral. Okay, and this lower integral, of course, is less than the upper integral, or equal to. Okay, so I'm doing this because we said right at the beginning our goal was that we wrote down sigma as just a generic Riemann sum, anything with norm q less than delta, and we wanted to show that that the absolute value of sigma minus this number, this was our I, is less than epsilon. So I've got one direction of that. This isn't an absolute value yet, so we need to try to go the other way. So we've bounded sigma above. Now let's see if we can bound sigma below. So to bound sigma below, I'm just going to do exactly the same thing, but in reverse. So we know that sigma is bigger than the lower sum, minus epsilon over 2. Okay, again, I can relate this lower sum back to my upper sum. So, okay, it's here. Capital S minus little s is less than epsilon over 2. That means that little s is bigger than capital S minus epsilon over 2. So this is bigger than capital S minus epsilon over 2. Okay, which we can simplify. Then same reasoning as before. We have all of these upper sums. They're all overestimates. So if we're trying to get our upper integral, we say these are all overestimates. So let's take the smallest one. And that means this is bigger than the upper integral. And then we still have our minus epsilon. So what do I have if I put this together? Sigma minus this upper integral, which I called I before. Okay, well, sigma minus this number is bigger than minus epsilon. And sigma minus this upper integral is less than epsilon. You agree with this? Okay, that's what I wanted, right? I have this number. It's constrained to live between minus epsilon and plus epsilon. That's exactly the statement that sigma minus this upper integral is less than epsilon. And this is exactly what the goal was. We wrote down on the first board right at the beginning. No, it was 45 minutes ago. 45 minutes ago, we wrote down this goal that we picked a generic partition. We weren't sure what delta was, but now we have a concrete value for what delta is. And as long as we take our delta to be this, we have sigma minus this number is less than epsilon. That is exactly writing down the definition of the Riemann integral. Okay, so I can conclude that f is Riemann integrable. And we know its value now. We know that the integral of f is actually equal to the upper integral of f. Okay, and if we do the same reasoning, it's just these last steps that I would have to repeat. Here I would say this upper integral is bigger than my lower integral. Over here I already had something that related it to my lower integral. The same reasoning gives the integral from a to b of f is equal to the lower integral. And that's what we wanted to prove. So, any questions on that? That was a long proof, right? But again, it's taking the building blocks that we have, the basic definitions of the Riemann integral, the basic definition of our upper sums and lower sums, and it's patching them together. Now, it's patching them together using a lot of different steps, but each step still taking our basic building blocks. And the good news is, okay, we've done all this work, and it was a lot of work, but we've done it once, and now we can use it forever after. There's no, I give you a new integral that you haven't done before, and you have to look at all possible Riemann sums over all possible partitions and work it out, which is messy. Now, we've done some work, but we've got a nice tool that we can use to make life a lot easier in the future. Questions? You look a bit stunned. Right, so let's go back to an example that we did last class. We did all the work last class already. E to the x dx. Okay, so we used, I'm just going to recall the highlights of what we did last class. We used a uniform partition. Okay, so P was x naught to xn, where each of these could be written as j times h, and h was 1 over n. Okay, and because this was a reasonably nice function, it's still nonlinear, but it's reasonably nice. We could work out exactly what the upper sums and lower sums were, right? We knew that because this was an increasing function, the capital M sub j always happened at the right endpoint, because the function was always going up. It hit its maximum at the right side. we wrote down the upper sum and we said, oh great, that's a geometric series which we can add up. And we found that the upper sum of f on p was going to be equal to, where is it? H e to the h times 1 minus e over 1 minus e to the h. And we found the lower sum. The lower sum was very similar. It just involved h times e minus 1 over e to the h minus 1. Okay, so we did this, and again, the reason we could do this was because we had a very simple partition. If I'd said do this on a generic partition, you would have been unhappy with me. Okay, and now we have some tools to let us analyze this. We also found that. Let us characterize this a little bit more. Let us call this p subscript h. So we found that we could take limits of these things as h goes to 0. And we found that the limits of these actually gave us the same thing. Right, so we had a simple partition, wrote down the sum, and we said we could figure out what these upper sums and lower sums do in the limit. That's great. And they happen to do the same thing in the limit. So we said that sounds hopeful. Again, we didn't know if that was going to give us the value of the integral or not because we'd done simple dumb partitions. And we had a definition of the integral that said you can't just do simple dumb partitions. Now we have a new characterization of the integral that says actually, yeah, you can, as long as you can control things. And it looks like we can probably control things because what can we say? These are both approaching the same limit. So that means, let's choose our epsilon. Okay, well then we know that there should exist some, say, h star greater than 0. Do I want to call this h star? I'll call it delta for you. There exists some delta greater than 0, such that as long as h is less than delta, right, then this guy gets arbitrarily close to epsilon minus 1. Then capital S minus e minus 1 is less than epsilon over 2, let's say. And little s minus e minus 1 is also less than epsilon over 2. Right, this is just the definition of the limit. Okay, and since these guys are both close to e minus 1, they're also very close to each other. So what do we know? We know that capital S on this partition minus little s on this partition, those are the things we have to look at. Well, this is at most e minus 1 plus epsilon over 2. Right? Capital S can't get farther away than that. And this, right, this again is close to e minus 1. And it can differ by at most epsilon over 2 in each direction. So the smallest this would ever be is e minus 1 minus epsilon over 2. And that's our epsilon. And then you're done, right? We did it on a simple partition. That was good enough. So in fact, it's good enough to get this far, right? I come up with a simple dumb partition. I come up with an upper sum. I come up with a lower sum. I show that I can make them both approach the same limit. Then I'm done. Then I can make this argument and conclude that, therefore, actually, yes, e to the x is Riemann integrable on this interval. And since these things both approach e minus 1 in the limit, is equal to e minus 1, which we suspected last class. Now we know. Yeah?
Two questions. One, if we can show this limit kind of behavior,
Yes.
do we have to walk through the rest of this each
If
time?
you can show this kind of limit behavior, you're done.
Okay. And then the other question was, so here we use the same piece of h to find a limit for the upper sum and the lower sum.
Yes.
If we found it more convenient to use separate piece, like one was good for the upper sum, one was good for the lower sum.
You have to use the same partition.
But if you had, but doing separate ones, you could find if they converge to the same value, even though they're separate partitions, then you have the upper integral and the lower integral.
Not necessarily. So when we use this to characterize the upper integral and the lower integral, when we proved the theorem that we just proved, we were assuming they were both given on the same partition all the way through.
Right.
So you do want them to be on the same partition. You don't want to do sort of sneaky magic where you pick a partition that's uniquely determined to make capital S as little as possible and pick another partition that's uniquely determined to make little s as big as possible. So this should be
But if you had those
uniform.
partitions,
Yeah.
wouldn't there be a refinement of both that would, like, satisfy both behaviors?
Would there be a refinement of both? That, okay, so why aren't you just using that refinement then, right?
Sure.
Yeah.
Okay.
Okay, so this is an easy example. Also, the example that you just did in your homework is very easy to do this way. You might have done it this way, which is totally fine. Right, so in that case, you might be able to just explicitly, I'm not going to write all the details, let me give you highlights of it. So this example, 0 to 1 x squared dx, right? You take, again, a uniform partition with xj equals j times h. H is 1 over n. Okay, you do an upper sum of this guy on this partition. And, okay, so for the upper sum, this guy is monotone increasing, so we're going to take the right endpoint, jh squared times h. And then you say, okay, h cubed I can pull out. This is the sum of the first n squared terms, and there's a formula for that. So this is really h cubed times n plus 1, 2n plus 1, divided by 6, which you can simplify down to 1/3 plus 1/2 h plus 1/6 h squared. Because h times n is equal to 1. Okay, same thing with your lower sum. You take the left endpoint. You get j minus 1 h squared times h. Okay, same deal. This is, okay, the first term is 0. Then it's 1 squared plus 2 squared plus n minus 1 squared. So the same formula just applied to n minus 1. So n minus 1 times n times 2n minus 1 over 6. And you get almost the same result. 1/3 minus 1/2 h plus 1/6 h squared. Okay, you look at the difference between them. And the difference between them, well, 1/3 minus 1/3 goes away. 1/6 h squared minus 1/6 h squared goes away. All that's left is 1/2 h plus another 1/2 h. And we can certainly make this less than any epsilon we like, right? As long as h is less than epsilon. We can always find a uniform partition with h less than epsilon, right? So then straight off, you conclude, great, this guy was Riemann integrable. We go back and take the limits of these things. The limit was 1/3. So therefore, we can conclude that f is Riemann integrable. And we know the value of the integral. Right? We take h to 0. All that's left is 1/3. Any questions on that? Better than doing generic partitions? A lot easier, right? So again, it was a lot of work proving this theorem, but now we know it, now we can use it. It makes life so much easier in many cases. So anytime that, I'll just summarize this, anytime that you're asked to prove a function is Riemann integrable, if I say use the definition of the Riemann integral, then that means we're really looking at all these possible partitions, all possible Cj. If I don't clarify, if I just say, show me that this thing is Riemann integrable, then you get to use whatever method you like that's correct. And this method is usually the easier method. But again, anything that's correct will work. So know what tools you have, know how to use all of the tools, but know which one is the easiest one to use. And this one is usually the easiest one to use. Can we think of some special cases of functions that are just automatically Riemann integrable? We don't have to do this work. We can just look at the function and say, yeah, this can be done. Continuous functions, okay. So yes, a continuous function will automatically be Riemann integrable. Can you think of any others? Piecewise continuous, okay, piecewise continuous, yep, you can always break up into subintervals and do them each separately. Any others? There was actually an observation someone made last class about why it was easy to pick out what our MJ was for a particular function. Monotonic, yeah. So some functions we just look at and we say, oh, that's Riemann integrable. I don't have to do any work to prove it. So theorem, let's let f be monotonic. I'm going to do this proof. This one is pretty short, so I'll do it in class on AB. Okay, then f is automatically integrable. And again, this is one-way kind of implication, right? Obviously, we know there are non-monotonic functions that can be integrated as well. So So you can't use it to go the other way around and say if I have a function that's bouncing around, I don't know, right? So let's let f be monotone on an interval. And I'm just going to suppose for this proof that f is increasing. You can do the same proof exactly with a decreasing function. Okay, so we know that as long as we choose x in this interval, this is always going to happen. Agreed? Okay. So f is bounded, right? I'm not assuming f is continuous or nice or anything like that. It increases, but it may do so in a very herky-jerky sort of way. But nevertheless, it's bounded, and it's bounded because we know that it's always less than the value at the right endpoint and bigger than the value at the left endpoint. So f is bounded. Bounded is good. We need bounded. All right, I want to show this thing is integrable. Again, we have different ways of doing it. We can use the old definition of the Riemann integral, which works, or we can use this new characterization we came up with, which says we can do simpler things. So let's do simpler things. We still need an epsilon. All right, I know that I want to use my easier characterization, so I know I'm going to need some upper sums and some lower sums. So let's define capital Mj to be the supremum on this little subinterval of f of x. And what's that equal to? F of xj. Because it's increasing, its biggest value is going to happen at the right endpoint. So this is f of xj. And we can similarly do the infimum. And again, since f is increasing, the smallest value is going to happen at the left endpoint. So this is f of xj minus 1. Okay, so again, I'm just trying to, we have a characterization of Riemann integrability. All I'm doing is writing it down, the thing that I need to compute. The thing that I need to compute is the difference between the upper sum and the lower sum. Okay, so S, my upper sum minus my lower sum. This is equal to sum over all these intervals of capital Mj minus the sum over these intervals of little mj. Okay, and of course we can combine these. This is f of xj minus f of xj minus 1 times xj minus 1. This is non-negative, yes? Again, the function is increasing, so the value here is always going to be bigger than the value here. This, what's the biggest this could be? delta, exactly. So this is less than or equal to the norm of p, whatever that is, which is less than some delta that we don't know yet. So because I have something positive here, I have a product of two positives, that means I can use this bound here. So this is going to be less than or equal to delta, actually strictly less than delta times this difference in my f's. All right, what does this sum to? F of b minus f of a. This is the same kind of telescoping series that we've seen before, right? I have, okay, f of 1 minus f of x naught plus f of 2 minus f of 1 cancels this, plus f of 3 minus f of 2 cancels the next one. This is our usual telescoping series. So we can write that down. Okay, so I've taken my upper sum minus my lower sum. I've gotten some bounds on it, a pretty simple looking bound. What was my goal? Make it less than epsilon. Can I do that? Of course I can. So this is less than epsilon, as long as we choose delta to be less than epsilon over f of b minus f of a. And that's it. We've just written down this characterization of Riemann integrability that says, as long as I can make this less than epsilon, I'm done. I'm in business. So right away I can conclude f is indeed integrable. Okay, so every time you see a monotone function, you know that it can be integrated. You don't know that it has a simple expression or a simple way of computing it, but you know it can be done. There's a value out there. Any questions on this? Yeah, George.
Given a monotone function,
Yeah.
just show that this is Riemann integrable?
Yeah.
We just say it's a monotonic function.
You could just observe it's a monotonic function. Yeah, again, unless I ask you to use a particular technique, every theorem that we prove in this class is fair game for your use. Okay, and then I'll write down the other theorem that you guys have already suggested to me, that if f is continuous, this can certainly be done. So if f is continuous on A to B, then f is automatically integrable. Again, it's not an if and only if, it's just one way. We can certainly do non-continuous functions. But if it's continuous, we can definitely do it. This one I'm not going to prove. I'll refer you to the book. It involves some properties of continuity that are a little more complicated than what we got into. So I'm just going to say, refer to the book here. It uses the concept of uniform continuity. Which involved some notions of compactness that I didn't get into. It's a little more complicated, but you're welcome to read it. It is all there in the book. But the idea is, again, that we have f at different points, right? The idea is we have f of cj minus f of dj. So we'll call this our mj minus our little mj. They don't happen at the endpoints anymore because it's not necessarily monotonic, but they happen somewhere because a continuous function always achieves a maximum and a minimum. So we can really do this. So we write this down, and then we bound this by using continuity. Right? Continuity says I can make this less than epsilon as long as Cj and Dj are close together. So you have to do it in a careful way, which is going to take more than the next 1 minute. So I refer you to the book here. Again, this is a theorem that is true, and you can use it. So I'll leave you there today. We'll do more properties of the integral next class.